Hello, Amir Khan again. So let's talk about what we're going to talk about today. So the agenda includes a very brief introduction to flex power modules, introduction to conducted and radiated emissions, testing methodologies and various considerations for that, filter design and simulating it, and summing it up for basic EMI filter design. And in the end, we will have Q&A. So a little bit about us. Flex Power Modules carries a strong history of producing innovative state-of-art power solutions since 1980, when it started out as a division of Ericsson in Sweden. Back then, these solutions were crafted to support our own telecom equipment, much like other big telecom names like AT&T Bell Labs. Fast forward to today, and with a wide variety of products, we enjoy a dominant supplier position in many industries. These include compute and data center, and of course, its fastest growing segment, AI, as well as telecom and industrial applications. We offer standard products in addition to a heavy focus on custom designs for our key customers, including the new vertical power delivery solution. To learn more, please visit flexpowermodules.com. So a little bit about myself. I've been in the power industry for over 15 years. I've been an FAE all this time. And during my tenure, I have come across EMI issues all this time and found them to be difficult to pin down and hard to solve for, which is why we are talking about it today. In this industry, I've been through many different phases of the industry in the last 20 years. Before this, I was in the semiconductor industry as well. So enough about me, and let me introduce our host, our speaker for today, Giorgio Mairi.
Hello, everyone. Welcome to the webinar. My name is Giorgio Mauri. I'm a Senior Principal Applications Engineer at Flex Power Module. I have nearly 30 years of experience in the power conversion industry. I've joined Flex Power Module 3 years ago. I've always worked as an applications engineer at several power supply companies, and also recently at power semiconductor companies. I think it's time to start our webinar.
Let's talk about conducted and radiated emissions. Conducted and radiated emissions are two parts of electromagnetic compatibility. The other two parts are conducted and radiated susceptibility. If we consider two equipment operating in the same EMC environment, one equipment is acting as a noise source and the other equipment is acting as a receiver. The two equipment are separated by a coupling path. The coupling path can be radiated emissions or a physical connection, for instance, through a common mains line. Electromagnetic interference is the noise generated by the noise source. Electromagnetic susceptibility is the capability of the receiver to reject that noise. Electromagnetic compatibility is the ability of the equipment to operate in the same electromagnetic environment without problems. A switch mode power supply is a noise source. Noise can be generated by electric fields and magnetic fields. Electric fields are proportional to dVdt, tends to be near field, so are attenuated by distance and coupled through straight capacitances. Magnetic fields are proportional to dIdt and are coupled by mutual inductance between nearby wires. Where ground is part of the wiring, the resulting current is common mode and gets radiated by large loop areas. Field strength depends on orientation, so it can be used to attenuate the effect of magnetic coupling. To limit the coupling mechanism, we may want to install the EMI filter close to a metal wall of the equipment enclosure at the boundary between the internal and external EMC environment. The enclosure acts as a shield for the complete equipment, but ideally, we may want also to isolate the EMI filter with its own metal shield, so that it is less susceptible to internal radiated noise. Shielding is one tool to limit radiated emissions, but getting the conducted emissions within limits is the best approach for successful radiated noise testing. Here we can see a typical conducted emission test result. A typical switch mode power supply voltage or current waveform in the time domain and its corresponding frequency domain spectrum. It's important to understand the relationship between time and frequency domain for common power supply switching waveforms. In general, we can say that the fundamental switching frequency and its associated harmonics tends to be differential mode noise. Noise associated with rise and fall time of fast switching waveforms tends to be common mode noise and tends to be concentrated in the higher portion of the frequency spectrum. Harmonics are found at integer multiples of the fundamental switching frequency. High frequency noise is characterized by sin x over x behavior. We have seen a typical conducted emissions test results, so let's see very quickly how conducted emissions are tested and one simple way to separate common mode from differential mode noise.
One very important thing to note is that in a conducted emissions test, we measure noise currents. The EMI receiver will report noise voltages by converting currents into a known impedance of 50 ohms by means of a line impedance stabilization network. So we are really looking at currents here. Before getting into the Listen description, let's define differential mode and common mode noise. The diagram is a very simplified illustration of a typical test setup for a three-wire systems, line, neutral, and ground. The definition is a legacy of AC to DC systems. We have a power source on the left, the EMI filter we want to design, and a noise source on the right, a DC to DC converter in our case. Noise currents are generated as you can see in the diagram. Differential mode currents flows in opposite direction in the input lines. It doesn't flow into ground and therefore exists in both 3 wires and 2 wires systems. So it's applicable to both isolated and non-isolated DC to DC converter. This is because it's associated with normal circuit operation, like the switching action of the converter. Common mode current flows in the same direction in both input lines and returns to ground. So it's present only in 3 wires systems and typically associated with isolated converter.
Here we can see the conducted emission test setup including the Listen circuit. A 6x16 Listen for testing according to EN 55032 is taken as an example. Listen characteristics are defined in EMC standards and selected depending on the standard we want to apply. A Listen accomplishes several functions. It separates the mains noise from the device under test. It separates the device under test noise from the mains. It provides 50 ohm source impedance to the device under test and 50 ohm termination to the EMI receiver. It enables measurements of noise voltages and simulates the typical line impedance. The graph on the left is the impedance presented to the device under test and shows it's a constant 50 ohm in the measurement range of 150 kHz to 30 MHz. It also shows that variation due to the 3 different values of source impedance taken as a reference are only present at low frequency, below the lower EMI test limit. The graph on the right is the impedance presented to the EMI test receiver. Again, it's a constant 50 ohm in the range of interest. As you can see from the equivalent circuits and circuit equation for differential and common mode noise, the actual termination impedance is different for the 2 modes. It's 100 ohms for differential mode and 25 ohm for common mode. This is something we need to consider, but most importantly, the line impedance stabilization network does not separate common mode from differential mode noise. This has an implication on the EMI filter design process, as we will see next. We design our EMI filter by mode separation. In other words, the common mode and differential mode filter circuits are different. The 2 modes typically have also different insertion loss requirements depending on frequency ranges. To determine those requirements, we need to know the actual contribution of the 2 different noise modes. The circuit in the diagram is the simplest circuit for the built-in Listen component, the symbol you can see in the top left corner. The circuit shows what we have seen in the previous slide with the equivalent circuits for common mode and differential mode noise. We have the Listen circuit on the left, followed by a buffered 50 ohm termination impedance. The buffered signal is fed to 2 summing building blocks, a non-inverting and an inverting one. Those two building blocks are separating common mode noise on the top side from differential mode noise on the bottom side. The two noise contributions are then summed again to provide both individual and total noise contribution in a simplest simulation, with some caveats. We can replicate those functions by using either a differential mode rejection network or power splitter combiners. The differential mode rejection network circuit is shown on the bottom of the slide, and suitable splitter combiners are listed. With splitters, we can eliminate one noise mode or another and determine the actual insertion loss requirements of each mode. With differential mode rejection network, we can do the same by following the 3 steps procedure described here. Insertion loss is one of the design targets for an EMI filter design. So let's look at some details. Insertion loss is determined with a 2-step process. First, we measure the noise power of our noise source without the EMI filter. Second, we repeat the measurement with the EMI filter in place. This is what FlexPower module publishes on its product datasheet, as you can see an example here. Insertion loss is then determined as the ratio in logarithmic units between the received power measured without the EMI filter to the received power measured with the EMI filter connected. It can be conveniently expressed in terms of impedance matrices, as you can see here, and that is because the terminal impedances can be directly measured. Otherwise, you can use S parameters taken with a network analyzer. Conversion from one matrix type to another is very common, and as we will see, using ABCD parameters is very convenient in the design process. Important things to note are insertion loss is the power loss due to insertion of the filter before the load, and it could be induced by attenuation, but also by impedance mismatch. Maximizing mismatch between different stages of a multi-stage filter is a common design objective. Insertion loss measurement is defined in the CISPR 17 standard. Insertion loss depends on both input and output impedances, and the CISPR 17 standard requires measurement with matched and mismatched impedances. The rationale is to consider a real-world situation where impedances are either not matched or not even known. The resulting set of measures will better illustrate the filter characteristics. This is a major difference for the design of an EMI filter when compared with the typical design procedure of narrow bandwidth signal processing filter or wide bandwidth matched impedances RF filters. The standard accounts for a measurement in a 50 ohm matched circuit and in circuit having mismatched low to high 0.1 ohm source to 100 ohm load impedance and high to low 100 ohm source to 0.1 ohm load impedance. A matched impedance doesn't happen very frequently, if not at all, and it's an optimistic situation in most of the cases. Low source impedance to high load impedance is realistic for most differential mode noise cases, while the other way around is more applicable to common mode noise. Unfortunately, exceptions tends to be the rule, to the point that actual testing with a real converter is usually advisable.
Let's look now at some filter design parameters. We can start with attenuation and output impedance. One important thing to note is that attenuation is not insertion loss. As we have seen previously, insertion loss is obtained with a 2-step measurement, with and without the EMI filter in place. Filter attenuation is obtained from the filter voltage transfer function. With some manipulation, we can reduce any filter to the simplest form illustrated in the diagram, which is a frequency-dependent voltage attenuator. Boundary conditions are, however, different than those we use for insertion loss, where input and output impedances are part of the equation. Attenuation is computed under the assumption of a low source impedance and a high load impedance. This might be true for op-amp-based signal processing filters, but it's not always true for EMI filters. From the EMI measurements without the EMI filter, we determine how much attenuation is required. The EMI filter is a low-pass filter, so we take the lowest noise frequency as our target. It is 1 MHz in this case. In general, this tends to be differential mode noise, and we label the noise as such in the formula. The noise amplitude exceeding the EMC limit in dB microvolt plus any margin we may want to apply is the required attenuation in dB. Typical design margin to account for variance over a large population of products is 6 to 10 dB microvolts. Once attenuation is known, we can select the filter order and determine an approximate cutoff frequency. There are situations like the one we see in this EMI scan, where a strong second harmonic may still exceed the limit, and we may need to adjust the filter cutoff frequency accordingly. The schematic at the top of the page is the typical EMI filter configuration using a common mode choke with its own leakage inductance split into two halves. Each leakage inductance is placed on each input line for symmetry. The EMI filter uses a single circuit to attenuate both common mode and differential mode noise. So we need to split the circuit into two equivalent circuits. Then we need to collapse the equivalent circuits to single-ended so that we can analyze easily. For differential mode, this is done by excluding the common mode inductance and including only the leakage inductance. Also, common mode Y capacitors are connected in series and parallel to differential mode X capacitors. Finally, inductances placed on opposing lines are summed together and placed on one single line to obtain the final single-ended circuit. Similarly, for common mode, we use the common mode inductance and we can eliminate leakage inductance and all the X caps. In this case, we have two differential mode inductances, basically two discrete inductors, each with its own magnetic core, placed on both lines. The two inductors are parallel for common mode noise, and this is reflected by half inductance value indicated in the single-ended schematic. The single-ended circuit we just obtained becomes easy to analyze, and we can write equations for attenuation and output impedance, and let MathCAD graph the equations for an easy visualization. Here we can see a MathCAD spreadsheet where the filter components values are entered and the two graphs are plotted. We can also add some nice features. Recalling our previous discussion about attenuation, we can set a target attenuation. Here is 42 dB at a specific frequency of 360 kHz in this case. This is plotted as a single dot in the attenuation graph, and we want the attenuation curve to stay on the left of this target attenuation. Also, we may want to include converter parameters like output power, efficiency, and minimum input voltage for a rough estimation of the converter minimum input impedance. I'm going to discuss the importance of the converter input impedance in the next slides. For the moment, let's consider this minimum input impedance as a design target, plot as a dashed line in the output impedance graph. The resulting value is actually a fraction of the minimum input impedance of the converter. This is done to account for some margins. Again, we will see next why this is advisable. We want our EMI filter output impedance to fall below the target line. So, we need to attenuate a certain amount of noise, but as we have seen, the filter attenuation we have just computed is not the attenuation we are going to get from our filter. We need to take input and output impedances into account and use insertion loss instead. Here we can see the difference. In this MathCAD spreadsheet, I'm using a simple second-order filter as an example. On the left side of the sheet, I'm computing attenuation, like we have seen in the previous slide, using the filter voltage transfer function and the assumption that the source impedance is very low and the load impedance is much higher than the filter characteristic impedance. Then, I'm repeating the voltage transfer function computation using a different technique. I'm using ABCD chain matrices or transmission matrices to include specific input and output impedance conditions. Recalling our discussion about CISPR 17, I'm using three different cases to illustrate the concept. Matched 50 ohm impedances, mismatched low input to high output impedance, and finally, mismatched high input to low output impedance. You can see the results in the second graph on the right. I'm also extracting one of the curves from the second graph and superimposing it to the first graph to compare the two results. This is the dashed line in the graph. It's time now for some important observations. The attenuation versus insertion loss definition is just a way to highlight the different boundary conditions, but it's not entirely accurate. In both cases, we are computing the voltage transfer function, just using different assumptions. On the left side, we are not considering input and output impedances, but we get an insight about the undamped characteristic of our filter. We can get the same information from the output impedance curve, but it would be less intuitive to grasp. This is one reason to have attenuation and output impedance on the same spreadsheet, as we have seen in the previous slide. This wouldn't be possible with a circuit simulator, as the simulation setup is different for the two different cases, and we would need two different simulations. We will look at this. On the right side, we are including a more accurate description of the boundary conditions, but we don't get the undamped nature of the filter. Damping is provided by the output impedance, but in reality, that impedance is the negative input impedance of a real converter, and the negative input impedance does not provide damping at all. In conclusion, we need both methods to evaluate our filter. When we define insertion loss, we said it's a power loss provided either by a real attenuation or by impedance mismatch. Attenuation is losses and mismatch is reflection. So, in a power processing filter, mismatch is more desirable than attenuation. And this is one reason why multi-stage filters are also more desirable. They offer more flexibility in introducing mismatch and are more suitable to the high noise amplitudes that are typical in high power applications. Maximum mismatch is obtained when the impedance of one stage is maximally different than the impedance of the preceding stage. As you can see in this combination of filter networks, a high series impedance source is matched, but I'd rather say mismatched, with a low impedance shunt element, a capacitor, while a low impedance source is mismatched by a high impedance series element, an inductor. Increase the filter order, that is the number of stages, for more of the same effect. Knowing the nature of source and load impedance is important. This can be a problem in the case of common mode source impedance, which is undefined by nature, as it depends mostly on parasitic elements like stray capacitances. ABCD matrices and the sequential element theorem are really valuable here. ABCD matrices are describing the relationship between the input and output parameters of a single two-port network or of cascaded networks. The sequential element theorem determines the attenuation of a series of cascaded two-port networks by summing in the logarithmic space in dB the attenuations of individual elements with the preceding elements lumped with the source. The individual contribution to insertion loss of each element in the chain is easily determined and can be optimized. We briefly introduced damping. Let's see now why it is so important for system stability. Here we have two low-pass LC filters. The one on top is the same filter we have seen before and is undamped. The second filter is the same filter with damping provided by an additional RC network. You can clearly see the difference in the graph on the left. Then we have a simple buck converter whose input impedance is plotted in the graph on the right. In the same graph, I've also plotted the output impedance of the two LC filters. The input impedance of the converter depends on its output power and its input voltage, and is minimal at maximum output power and minimum input voltage. This is the worst case operating point of the combined filter converter system. The converter input impedance is also negative due to the constant input power nature of the converter. The horizontal part of the input impedance curve towards low frequency is proportional to the converter output load. The ascending part towards high frequency is proportional to the inductance of the averaging LC filter. The negative peak at the resonant frequency is proportional to the capacitor ESR. I have set the LC filter and the converter parameters so that the output impedance of both filters are very close to the input impedance of the converter. In the case of the damped filter, the output impedance remains below the converter input impedance. In the undamped filter case, peaking causes the output impedance, the dashed line, to cross the input impedance curve, thus resulting higher in a limited band of frequencies. This is where oscillation may occur. The condition for the EMI filter DC-to-DC converter system to be stable is the output impedance of the filter shall be lower than the input impedance of the converter. See the formula on the right, where D is the duty cycle and N is the turns ratio if the converter is based on an isolated buck topology. It is 1 in this case. So peaking can be a problem as it raises the output impedance of the EMI filter and may result in an unstable system. Lowering the Q factor of the EMI filter below 2 and placing its resonant frequency below the converter averaging filter resonant frequency are two common solutions to the problem. The discussion about filter output impedance is obviously applicable to the differential mode portion of the EMI filter. The multi-stage filter in this schematic is a good example of a typical application. If we recall our discussion about filter equivalent circuits, this filter configuration may result from a large common mode choke connected on the output side of the filter, so that the small output inductance in reality is a leakage inductance. Similarly, the RC network can simply represent a large electrolytic capacitor with its own equivalent series resistance. The correct ratio between inductances and capacitances and the proper selection of the damping resistor all contribute to a flat output impedance with limited peaking in the attenuation curve. A multi-stage design is more flexible in the choice of the common mode choke, which in a single-stage design would otherwise need to provide all the series impedance mismatch for both common mode and differential mode attenuation. A circuit simulator like Simplis can easily handle complex multi-stage filters that would be unmanageable with simple analytical techniques. It can also enable the inclusion of components parasitics for a more faithful representation of a real circuit. The schematic on top is the simple equivalent circuit obtained by mode separation and collapse to single-handed. R1 in this case is a discrete component and not an ESR. The schematic at the bottom of the page is the same circuit but including component parasitics. Simplis provides multi-level component models where more parasitic elements can be entered by selecting a higher level model. Here we can see the multi-level models of inductors and capacitors. In both cases we can enter the parasitic series resistance, DCR for inductor and ESR for capacitors. The capacitor model includes ESL with its own leakage resistance to approximate the component Q, but in most cases the series RLC circuit illustrated in the schematic is sufficient. The inductor model includes a shunt resistance but no parasitic capacitance to approximate the self-resonant frequency behavior of the component. This can be added manually and we will see how to determine the proper value. Other unimportant components like RC circuit to simulate the electric absorption are not modeled. This is a reasonable model for a wide bandwidth simulation. Vendors of SPICE models, sub-circuit or S parameters are more appropriate when higher accuracy or wider bandwidths are desirable. The most important parasitic element we have seen so far is the common mode choke leakage inductance, as it becomes part of the differential mode filter. For a full bandwidth circuit model, 5 different measurements would be needed to characterize the common mode choke. The common mode choke equivalent circuit is surprisingly complex, and I'd rather refer to an excellent paper for a complete description. For our simulation purposes, 2 individual measurements of common mode and leakage inductance are sufficient. We can also limit our measurement bandwidth to 50 MHz so that we can use the Omicron body 100 frequency response analyzer. Here you can see each test setup and how those measurements are carried out, either by paralleling the two windings for common mode inductance or by connecting them in series between the instrument source output and the input for leakage inductance. An actual measurement is often necessary because not all the component vendors provide a full set of data. From the measurement we have taken, we can see that the leakage inductance approximates quite well the ideal inductor behavior, a straight line from few kilohertz up to nearly 30 megahertz. Let's focus now on the common mode inductance and how to derive its equivalent circuit model from measurement. The measurement in the top right corner of the page shows the common mode inductance is much less ideal than the leakage inductance. The self-resonant frequency is between 1 and 2 megahertz. Below this frequency, the component behaves like an 180 microhenry inductor. But above 2 megahertz, we can see a more complex behavior. The equivalent circuit model is a simplified lumped element SPICE model published for a different component, but equally valid for the component under test or for any inductor in general. The inductance L var and damping resistor R var 2 are both specified as a function of frequency. Another resistor R var 1 is specified similarly, and it probably models core losses as function of frequency. We would need more testing to find out. I'm using the reactance chart to identify each circuit element. The reactance chart is a log-log chart for X and Y axis and has two additional log-log axes tilted by 45 degrees with respect to the main axis. Frequency is reported on the X axis. Resistance is reported on the Y axis. Inductance and capacitance are reported on the plus and minus 45 degrees axis respectively. The first element to be identified is the inductance L var. Capacitor C is identified by using the self-resonant frequency, and R var 2 and R1 are identified by their respective resistance level. Once the elements are determined, the circuit can be simulated in SPICE for a more accurate representation. See the graph on the right. Note that peaking is not modeled with the reactance chart, but the resulting graph is, however, similar to the SPICE simulation. The graph on the top left is a class 2 multi-layer ceramic capacitor impedance chart and is replicated on the right using SPICE. I'm using a Murata 1 microfarad 100 volts X7R capacitor in an 0805 SMD package as an example. I'm including formulas to estimate component values analytically. It's easy to identify capacitance, self-resonant frequency, ESR, and inductance. The SPICE simulation shows the circuit queue and how to identify individual parameters. Multi-layer ceramic capacitors can operate over a wide frequency bandwidth and are excellent components for an EMI filter. The high capacitance value necessary for EMI filter usually precludes the use of class 1 capacitor, also known as MP0 or C0G dielectric, with vanishingly small dependence upon temperature or applied voltage. Class 2 capacitors have much higher capacitance per unit volume product, but are also less linear with temperature. Most importantly, their capacitance is AC and DC voltage dependent. The so-called DC bias voltage dependence is highly undesirable, and the graph for a TDK 4.7 microfarad 100 volts X5R part in a 0805 SMD package shows the effect. The nominal capacitance is only available with zero DC voltage applied, while in the typical input voltage range of a 48 volt DC to DC converter, from 40 volts to 60 volts DC, only 1/10 of the nominal capacitance is available. The DC bias curve is difficult to derive analytically as it depends on the specific dielectric material. Some vendors are offering SPICE models or subcircuits, including the voltage dependence. In an EMI filter design, we can simply pick the worst case capacitance value at the maximum input voltage. Let's now have a look at a real EMI filter design. The schematic in the top left of the page is the EMI filter we publish on the BMR 316 datasheet. The BMR 316 is a non-isolated, unregulated 1 kilowatt DC-to-DC converter with a 4:1 voltage transformation ratio, 48 volts in to 12 volts out. It uses a resonant LLC topology switching at 1 megahertz, and it's typically used in data center computing boards using 2 steps power conversion. Its natural output load is a 12 volts in voltage regulator module supplying high power GPUs or large system on chips for AI. You can see the list of filter components under the schematic. In my simulation, I've replaced the original components with similar parts having available SPICE models for convenience. I'm using a Coilcraft inductor with the same equivalent circuit we have seen before, now with actual values provided by the supplier and calculated at 1 megahertz. Same goes for the ceramic capacitors. Capacitor C3, originally 100 microfarad, is replaced with an 82 microfarad Oscon capacitor. This is a capacitor type we haven't explored yet. Oscon is a Panasonic trade name for a solid conductive polymer aluminum electrolytic capacitor. It has excellent temperature and frequency characteristic and very low ESR, making it suitable for power supply designs. Here you can see its impedance and ESR graph. The first and foremost the simulation is the EMI filter output impedance. In the typical design process, we need to get it right to ensure proper system functionality before we can tackle the noise attenuation. I'm entering all the parasitic components, and I'm using the quantity feature of simplest multi-level models so that I don't need to enter multiple symbols for the parallel caps. Note that I'm disabling and shorting the 2 series resistances R1 in the inductor models. I'm doing so because those resistors are calculated at the single frequency of 1 megahertz and are not realistic in a swept frequency simulation. They would result in an unrealistically high output resistance at low frequency. Note also the disabled and shorted resistor in series with the Oscon capacitor. We'll see the effect of that damping resistor in a moment. For the AC simulation, I am shorting the input side of the EMI filter, and I am setting the output current source of 1 amp as a stimuli so that the output graph is directly plotted in ohms. The y-axis is then set in the milliohm range. The simulation calculates the frequency response of the parallel combination of Z1 connected in series with the source with Z2 connected in parallel with the load, similarly to the voltage divider circuit we have seen when we discuss attenuation. I run the simulation 2 times, without damping resistor and with the resistor in place. The solid line is the undamped configuration, and the dotted line is including the damping resistor. The output resistance is quite low, but the difference between the 2 cases is a non-negligible 4.5 dB. What is the impact on system performance? A transient response simulation can be used to investigate the system response. This is a simulation technique I've learned on Christophe Basso's website, highly recommended. Here, I want to see the effect of the filter output impedance when connected to the negative input impedance of a converter. I don't want to use a converter switching model with a pulse load applied to its output because I want to keep the simulation to the bare minimum. Instead of using a pulse load current, I can use a pulse input voltage and model the negative input resistance of the converter with a voltage piecewise linear resistor. A realistic pulsed voltage waveform is defined in a susceptibility standard, EN 61000-4-29, and it exercises the full converter input voltage range from 40.5 volts to 60 volts and vice versa. You can see the details in the simplest configuration window. The PWL resistor is computed with a simple Excel table and entering in the corresponding simplest model. Note that I'm modeling the BMR 316 as an ideal DC transformer, and the negative input resistance is that of the downstream voltage regulator module. Again, solid line without damping and dotted line with damping. Here, you can see a much more significant difference. The transient response without damping has severe over and undershoot behavior, to the point that the voltage presented to the input of the downstream voltage regulator exceeds its maximum input voltage of 15 volts. Damping fixes the problem, but not completely. A small 0.6 volts overshoot is still present. So, do we really have a problem here? Well, we shall take those simulations with a grain of salt. First, I'm driving the converter to the maximum input voltage. This is a bit unrealistic, as only an overdamped system would pass the test. Typically, voltages above 55 to 57 volts are not operational for this type of products. Second, the susceptibility standard is written for a different test scenario. And it's really stressing the system here, which is the objective of the simulation, by the way, to find limits. It would happen in a real-life situation. As a side note, the ideal DC transformer model is also pushing the limit. I should have included a parasitic output resistance and maybe inductance, etc. In conclusion, even if the problem might be less severe than it appears, a well-damped filter remains preferable. Last but not least, let's see the filter attenuation simulation. Here you can see the complete filter schematic and note that the input capacitor has been disabled because it's shorted by the zero output impedance of the input voltage source. Again, attenuation depends only on output impedance, and I'm using an approximation here. The filter insertion loss can be determined from the published EMI scans. We have 62 dB microvolt without the filter and 35 dB microvolt with the filter. Insertion loss is 27 dB. The attenuation predicted by the simulation is 50 dB, a very large but not entirely unexpected 23 dB discrepancy. We are not considering the proper boundary conditions and probably some parasitic element of the test setup, like coupling in the PCB layout, etc., not evident from component modeling alone. The next step would be to compute the same voltage transfer function with ABCD matrices and including input and output impedances and see if we get a better match with the test results. Interestingly, enabling the damping resistor in the simulation, the dotted line, reduces both the attenuation and the discrepancy by approximately 9 dB. After all, the tested EMI filter might be more damped than the virtual model. As usual, a simulation can only be as good as the model used to set it up. Time to draw some conclusions. In summary, this is the EMI filter design procedure we have seen so far. First, we need to determine the design requirement. For an EMI filter, those are insertion loss and output impedance. The input data for insertion loss is the reflected noise current from the DC to DC converter. This is available from the published EMI measurements, and the noise limits from the EMC standard, including the Listen impedances. For the output impedance, the input data are the DC to DC converter input impedance. Second, we need to determine the differential mode and common mode attenuation requirements separately. So we need to measure common mode and differential mode noise using either a power splitter or a differential mode rejection network in the actual test setup. And then we need to estimate or measure the common mode noise source impedance. Third, we need to determine a suitable filter configuration. We need to select a topology, including damping, which is very important, as we have seen. Then we need to characterize the suitable filter components and include all the parasitic elements. Finally, we simulate the filter output impedance, and we need to check it's much lower than the converter input impedance. We simulate the attenuation using the voltage transfer function, and we check with insertion loss simulation using ABCD matrix and the sequential element theorem. Finally, we check the filter transient response and make sure that the overshoot and undershoot are within desirable limits. This is an iterative process. We need to make modifications until all the three design parameters, output impedance, attenuation, and transient response, are satisfactorily met. And finally, we need to test an actual prototype. And usually, because of the very complex nature of EMC testing, in many cases, there will be a discrepancy. So we need to test and start over again with better assumptions. In conclusion, what are the most typical design pitfalls? This is a compendium of mistakes I've already made and I'd rather avoid moving forward. 3 different categories. First, design methodology. We need to pay attention every time we use an approximation. Insertion loss calculation is one example. Second, topological mistakes. Using a general purpose filter designed for a different set of requirements. This is very usual in AC to DC application using off-the-shelf filters, for instance. Selecting a topology that doesn't include damping is another example, and reusing the same common mode choke for 2 different stages of the same filter is attractive from a procurement perspective, but mistaken from an engineering one. There is no mismatch. Third, system design mistakes. Bad implementation of an otherwise good design. An EMI filter bypassed by parasitic coupling or by radiated noise. Time for the Q&A session now.